Hey everyone, so this week's lab video is going to be a little bit longer than most of the lab videos, in part because we've hit a point this semester where we're going to be tackling some topics that we can't tackle in the way that we would ordinarily tackle them because of the pandemic, because it's not a good idea for us to be doing a lot of breathing in indoor shared airspace. So what I'm going to do is I'm going to kind of introduce the lab, and I'm going to run through some of the procedures that we would ordinarily do, and then towards the end I'm going to talk about the procedures that we're going to use instead for our larger goal, which is understanding coordinated changes to breathing and heart function in response to exercise. So this lab activity ordinarily would start out with just learning a little bit more about methods for quantifying different aspects of breathing and heart function at rest and under various different conditions. So kind of the first thing that we would typically do is quantify carbon dioxide production at rest. And I just want to show you this method because I think it's kind of cool and kind of fun. Just to give you a sense of if you really wanted to quantify how much CO2 a person's producing, either at rest or under various exercise conditions, how could you actually go about doing that? Well, one way takes advantage of the production of bicarbonate, and that is it involves a solution of an indicator solution here called phenol red. So phenol red is a dye, totally non-toxic. And right here I've got just 2 beakers of phenol red. And as an indicator solution, the fun thing about phenol red is that it changes color as it becomes more acidic. So basically what I could do is breathe into this liquid for a set period of time. It's going to change colors in response to my breathing into it for a set period of time, and then I can use a sodium hydroxide solution to titrate it back to the original color, and then the volume of sodium hydroxide that I've added back as I'm titrating back to the phenol red color is going to be proportional to the amount of carbon dioxide that I've produced. So we could use this technique to measure, okay, how much carbon dioxide am I typically releasing when I'm at rest, and then we could run the same procedure after exercising to characterize the extent to which my carbon dioxide release increases as exercise increases. But so just to show you a little bit more of what this looks like. So here's my beaker. What I would do is I take this beaker and I'm just going to breathe out into the phenol red for 60 seconds. All right, now I have to admit I've lost a little bit of track of time, but if you had a second person there to time you, hopefully you can see that this solution has now changed colors quite a bit from the original red solution. So the next step would then be to take some sodium hydroxide and work with a known volume. And then pretty much what I can do is take that sodium hydroxide, add it back in, and takes a little bit of swirling, but we're not back to the original red. Swirl again and titrate back until I return to the original red, and then I have an index of how much carbon dioxide I produced. So that was really the first goal of this lab. So practice learning about methods for quantifying carbon dioxide production. We're actually going to see some other methods for quantifying carbon dioxide a little later on in the semester. The next part of this lab involves characterizing breathing and cardiovascular responses to changes in carbon dioxide and oxygen. And so for this exercise, what we would ordinarily do is we would take a finger pulse transducer, right? So a finger pulse oximeter. And before the pandemic, not that many people had worked with finger pulse oximeters, but I think as a result of the pandemic, people now know a lot more about them because they're actually a really excellent way of tracking your blood oxygenation levels with some caveats. But for this, basically what you'd want to do is you would record your heart rate, your pulse rate with one of these, and then this also provides an index of your blood oxygenation level. So right now this is giving me an oxygenation readout of 99%. So it's 99% saturation relative to fully oxygenated blood, maximal oxygen it could carry. So for this, you'd start out measuring your heart rate, your blood oxygenation level, and then also at rest or at baseline, how many breaths you typically take per minute. And you could do this just by counting breathing rate over a 30-second time period, then multiplying by 2. The next part of this exercise, so then we've got this changes in carbon dioxide and oxygen here, is, okay, well, how do we examine responses to changes in CO2 and O2? And for this, we're not going to do the same thing we did with the reptiles 2 weeks ago, where we blew elevated CO2 in front of the reptiles' faces. Instead, we're going to do something that, in childhood you probably learned you should never ever do, which is a rebreathing exercise. So what I have here is just a little mouthpiece attached to a 1-gallon Ziploc bag. I can start out with some air in here, and you'd use the same method with a finger pulse oximeter and someone helping you count number of breaths per minute. And over a 3-minute and 30-second time period, every 30 seconds you'd take a recording of your heart rate, breaths per minute, and your blood oxygenation reading. So that's literally this, right? I don't want to spoil the entirety of this, so what I want you to do now is just jot down a note about what you expect to happen to those measurements over time as you go through that rebreathing exercise, if you were able to complete it. And so not just what you expect to happen, but why you expect that to happen. Thinking about what you know about the regulation of breathing in response to changes in alveolar gas partial pressures, okay? So then the next part of this lab, it's something we can't do here with the equipment that we have available, but it's a comparison of this exercise to cases where both carbon dioxide and oxygen simultaneously decrease. And so there's some data in the lab handout that I'm going to give you that shows a sample set of responses to simultaneous decreases in carbon dioxide and oxygen. The third goal in this lab is to learn how to quantify respiratory volumes. And the main tool for quantifying respiratory volumes is called a spirometer. So a spirometer consists of a mouthpiece that looks like this that has a piece of fine mesh in it, and when you breathe in and out through a spirometer, it distorts the airflow around that mesh, and that airflow distortion gets picked up by a spirometer unit like this one here. And these spirometer units plug into an interface with our Power Lab units so that we can quantify breathing volume. So we're going to change views here and take a look at how the spirometer readings look on lab chart. And we're doing this because this is kind of going to take our lab chart skills to the next level. Okay, so here we are ready to get started getting things set up to measure breathing volumes. So what I have here is, here's my spirometer mouthpiece. It's attached with these two pieces of tubing onto my spirometer, and this has a very familiar looking plug that will just plug into input number 1. Then I can turn on the Power Lab unit. Got a green light here, so I'm ready to fire up lab chart. Okay, here I've started up lab chart, and in this case I'm going to simplify things down, so we're just looking at channels 1 and channel 2. The next thing I'm going to want to do is, for channel 1, we're going to change the input voltage here to 1 volt instead of 10. Okay. And then let's just do a starting recording just to see what this looks like. Okay, so I'm going to start running lab chart, and then I'm going to put the spirometer mouthpiece in my mouth, and I'm going to hold down this button on the spirometer, and I'm just going to take some normal breaths in, and I'm just going to breathe out a resting volume. So that should be equivalent to my tidal volume, right? Okay, so to press this button, and I'm just going to breathe out. Okay, looks like it works. I'm going to stop, auto scale, and let's take a look at some things here. So at this point, what we need to do is, this is giving us an index of the flow rate, right? And if we know flow rate and we know how long we're measuring, it's possible to calculate a volume. So for example, if our airflow rate when we're breathing out is 1 liter per second, and the flow runs for 10 seconds, then we know the total volume is 10 liters. That's pretty easy to calculate for a constant flow rate, but from testing the spirometer, I think what you can notice here is that the flow rate changes as you're breathing, right? So you breathe out more rapidly at first, and then that tapers off as you breathe. And so how can we get our tidal volume from this type of measurement? Well, this is where calculus actually comes in handy. We can get that by integrating. The great thing is we don't have to integrate this by hand. We can just get the computer to integrate it for us. So what we're going to want to do now is first we're going to want to correct our units. So far we've just been working in arbitrary units of millivolts or volts, but we actually want to convert this into volume units. So what you'll notice on these spirometer units is on the back of them there's a little calibration readout, and it's a little hard to read here because it's a bit blurry, but this says 1 liter is equal to 0.13 volts. So we can actually set that calibration on lab chart by going to the channel menu and then coming down to where it says units conversion. And in this menu we're going to use a 2-point calibration, and the first point in our calibration is 0. So 0 millivolts is equal to 0 liters. And then we're going to use this second part for our second point. So 0.13 volts is going to be 130 millivolts, and that is equivalent to 1. And then for our units, we're just going to put liters. Okay, and we're going to set that for all and new data. So when I click OK, what you're now going to notice, it's a little funky looking at the moment, but in channel 1, my axis label has now changed to liters instead of volts. Okay, so that's step 1. The next thing that we're going to do is we're going to calculate these volumes. So we're going to integrate in another channel. We're going to use channel 2 as our integration channel. So in the channel 2 drop-down menu here, you'll notice that there is an option in this menu for cyclic measurements. And so this is going to look similar to one of the other options menu we saw earlier, but it has some distinctions to it. First off, we're going to use channel 1 as our source channel. And in this case, our measurement is going to be height rather than rate, okay? So then the last thing we want to set here is under this preset menu, we're going to scroll down and we're going to use a preset for respiration airflow. So I'm just going to click that preset. And then if you click OK, we're going to go ahead and continue with what we have here. What this is now putting out is the integral of channel 1. And so let's look at the way to read this. And actually it's easiest if I do some additional breathing. So I'm going to start breathing again. So I've started this up. And I'm holding down the spirometer button. Okay, and I'm just going to do a series of breaths and watch what happens in channel 2 as I take these breaths. So I hope what you can see is that these integrals are lagging behind the recordings in channel 1 because they can't calculate on the current measurement. They're dependent on a time frame and a peak to integrate. But what you can now do with channel 2 is if you, for example, if you took the mean across this measurement window here in channel 2, that would give you the mean area under each of these peaks. And I would tell you that my average tidal breathing volume right now is somewhere between 0.2 and 0.3 liters, so about 250 milliliters as I'm breathing here right now. So having seen that, hopefully that gives you a way to imagine or how else you could use the spirometer to measure other aspects of your breathing function. So for example, if you wanted to measure your expiratory reserve volume, what you could do is breathe in normally, breathe out, and then force air out of your lungs and measure that, and that would tell you your expiratory reserve volume. And you can probably imagine a similar exercise for measuring your inspiratory reserve volume, and collectively that would allow you to figure out what your overall vital capacity is. So what volume, to what volume you can maximally breathe in, to what volume you can exhale. So what's the total volume that you can exchange in your lungs maximally. So obviously that type of breathing exercise, without a mask on, into a confined tube, the confined set of tubes, is really not a good idea when you're in the middle of a global pandemic caused by an airborne respiratory virus. So we can't use the spirometers this semester to measure our lung capacity. Thankfully, there's another tool that we can use instead that can provide us with a similar index of lung function. And that tool is a device known as a pneumotrace. So the way the pneumotrace works is it's got a couple of Velcro spots on it. And this is a stretch detector. So what you can do is put this pneumotrace belt on in a place where it can detect changes in volume between when your lungs are at rest versus when you've taken a breath in. So that's basically just applying it around your rib cage. And you want to put it on fairly snugly. And then it's got the same type of connector. So we can just plug this into channel 1 and we start recording. As you see, every time I take a breath in, measurement increases, and then as I breathe out, that measurement decreases. And of course it's going to be a little bit funny right now because I'm using it while I'm talking, but let's look, for example, at if I take a really big breath in, so the pneumotrace can also give us a quantifiable metric of our breathing volume, and also we can use it to calculate our breathing rate. And we'll want to apply a similar transformation as we did for the spirometer and report that out in channel 2. Okay, so the pneumotrace is going to give us a measure of breathing rate and a relative index of breathing volume. We're not going to be able to convert to absolute units like we could with the spirometer, but we still get relative information about breathing function. And these are fairly comfortable to wear both at rest and when exercising. So the other piece of information that we need, however, if we want to examine coordinated changes to breathing and heart function in response to exercise, is some method for characterizing heart function. So, when you exercise for breathing, there are two aspects of breathing that can change, right? Breathing rate and breathing volume. There's an equivalent potential for change for heart function when you exercise. So your heart rate could change, and also your heart's stroke volume could change. Measuring stroke volume is a very invasive procedure, so it's not something that we can directly address here. So the best that we can really do is simply measure heart rate. I've already showed you one tool that we can use to measure heart rate, right? So that was the finger pulse oximeter. So that could give you one index of heart rate. But if you want to study coordinated changes in breathing and heart rate, it would be very convenient if you could also get a measurement of your heart rate on lab chart that would correspond with your measurements and changes to breathing rates. So to do that, we're not going to set up a full EKG, but we're going to use some of the instruments that are available with our Power Lab kits that are going to let us measure the electrical signal produced by our heart every time that our heart beats. And so in the Power Lab kits, what you're going to find is a set of clamps that look like this, and they actually have an electrical surface on the inside right here. So these are fairly easy to clamp onto your wrist or also onto your ankle. So we're just going to work with 2 of these for the time being. And to improve the electrical signal, the other thing we'll do is we're just going to apply a little bit of this electrode cream. This is something we can wash off with salt and water, non-toxic. Just going to apply a little bit of electrode cream onto these clamps. Spread it around so we have really good contact. Then, for right now, I'm just going to clamp these on my left and right wrists. But another option is going to be to clamp them onto a wrist and onto an ankle. Okay? So I clamp those on so they're in contact with my skin. Then there's a set of leads, shielded leads, in the Power Lab kit. And these are all color-coded, and so we're going to take the color-coded lead, this one's green, and it actually just snaps right on to the end of this clamp unit. And the same thing with the red lead. So this red lead's going to just clamp right on to this wrist unit. Okay? At the other end are a set of plugs. And these plugs are going to plug into a bioamp adapter. So this bioamp adapter looks like so and has a plug like this. Okay, and we're just going to match colors together. So we'll put the negative with negative. The green is typically, by convention, a ground, so green in green. And then the other end of this cable plugs in on the Power Lab on the bioamp unit at the end. Okay? So now, all right, I'm all wired up. I'm going to press start. Got tons of wires going here. Let me bring you in a little closer. Okay. I'm going to press start. And if my electrodes are good and greasy, might not be yet. I also have to hold still. Should be able to see in channel 4, those little spikes are electrical impulses from my heart. If I switch the orientation of these electrodes, then it sometimes is easier to track the positive pulses rather than the negative pulses. And you may have to play around a little bit with putting the electrodes on your ankles, switching wrists to figure out a configuration that gives you a good signal. And it might also mean that you need a little more electrode cream just to get a really good connection with your skin. Our skin's not that great at conducting electricity. So now what I'm going to do is I'm just going to take a minute at rest. I'm going to breathe, and I'm going to try to get a clear recording of my breathing rate, my breathing volume, and my heart rate together. Okay. So I've still got a bit of work to do at this stage to analyze my breathing rate, breathing volume, and my heart rate, but hopefully this gives you an idea of how to collect some baseline data at rest. And from here, the next thing you're going to want to do is collect heart and breathing data after exercise. So we're going to keep things pretty simple for that part of lab this week. What you're going to want to do is set your treadmill for an intermediate speed. So it could be something like setting number 2. And then you're going to want to arrange everything so that you're still hooked up to the power lab, and then spend 60 seconds exercising at level 2, then pause and take a recording of your breathing and your heart rate for about 30 seconds. Then you're going to resume another 60 seconds, another 30 seconds, and repeat at least one more time, 60 seconds, and then another 30-second recording. This is going to take some collaboration with one person at the computer while one person is being measured. Then you want to rotate group members so you get exercise measurements for all of your group members. So when you're finished in between users with these electrode clamps, you just want to rinse these off with soap and water so they're ready to go for the next person. And lastly, I may wind up making a couple of changes to the exercise measurement procedures since this is a new process for me, just as it's a new process for you. So stay tuned for some updates on how we're going to go about these measurements when you get to lab on Tuesday. Okay, so I've showed you how you can use a phenol indicator solution to quantify carbon dioxide production at rest. Showed you how you can characterize breathing and cardiovascular responses to simultaneous changes in carbon dioxide and oxygen. Shown you that you can use a spirometer to quantify respiratory volumes, or you can use a pneumotrace unit to get relative changes. And I've also shown you that you can quantify breathing and cardiovascular changes in response to exercise using a combination of a simple electrode setup and a pneumotrace. So we're getting practice with these tools in this lab, and then your mission for the next lab is going to be to design an experiment that tests something associated with changes to breathing and cardiovascular function in response to exercise. So for the purposes of that exercise, I want you to think about a couple of questions. First question is, how might animals coordinate delivery systems to facilitate increased energy expenditure during exercise? And more specifically, we want to think a bit more about what do we mean by coordinate delivery systems. More specifically, how are breathing and circulation coordinated during exercise? Okay?